but as a class, you know, the people, the 3 people that actually showed up to class today here live and in person don't really have any questions from 2-6. They thought the videos helped. So I'm going to open it up to the audience, see if there's anything in particular you had questions on, or odd exercise, or even one of the evens that I said was supposed to be due today. Any questions, concerns, issues, problems? One you want me to do just for fun? Nothing? Liking the videos? I'm starting to loosen up a little bit. I'll get a little looser as I go too. They've improved. First ones were more catch up. So there's no questions. So, I mean, really? No questions at all? Okay. So 2.7, we're getting into trig stuff. So let me, I'm gonna switch over. Let's do this a little bit. Has anybody watched any of the videos in the trig deal? Probably not. No? You had other stuff going too, I know. So, all right. I'm gonna share my whiteboard here. We'll just do it this way. Oh, you guys can't do that. Never mind. No, I don't want to. That's right. I got most of it's in. I'll just talk it out. Let's see. Where'd I go? Okay. How do I go back to me? Can you guys see me on your at home? Or wherever?
Yeah, I can see.
Okay. Kylie's here. Oh. Well, Kylie, how are you doing? All right. So good. She's fine. Perfect. All right. Well, I'm just going to go to the board here. We're going to do some of this is in your videos, but these are things that you need to know inside and out. So in calculus, you know, we went through the trig stuff, right? So we have a little trig timeout in this section, but we're going to take the derivative. I'm going to do it with respect to t. So a lot of times we'll use t for theta, but the derivative with respect to t of sine of t. So sine of t or sine of theta or sine of x, really it's a dummy variable. You just don't be a dummy, right? Anyway, so the derivative with respect to t of sine, derivative of sine is pretty easy. It's cosine of t. So this is instantaneous rate of change of the curve at a point. So we can actually prove this, but you just can accept it as a fact. The derivative of sine is cosine, which is kind of nice. So, and it's the kind of the way the curves work out there. But then we also have the derivative of cosine. Derivative of cosine is minus the sine of t. Okay, so the instantaneous rate of change of cosine is the opposite of sine of t. So if we have a particular point, we could do that. So like if I wanted to plug in a certain angle or something of that nature. So anyway, so we have these two things. So pretty basic there to know that, right? You do need to know them, memorize them, make sure you know them. Anyway, so what other trig functions do we have? Secant. Okay, so the derivative with respect to t of secant, the derivative of secant is actually secant t tangent t. Secant t times tangent of t. So the derivative of secant is secant tangent. When I say them out loud, I don't say the variables there too, but it's, you know, secant t tangent t. Okay, so that's derivative of secant. So the derivative of cosecant is very similar. And if you notice, whoops, cosecant would be CSCT, CSC for cosecant. Okay, so what happened when we had derivative of sine was cosine, then when we took the derivative of cosine, we had a minus sign there, right? So when we had a co, there was a minus. And that's going to be showing up again. So here, this is cosecant, so there's going to be a minus. And instead of secant tangent, it's going to be cosecant cotangent. So if you know one of them, it's easy to figure out the other one. So anyway, this is so it's the derivative of cosecant is minus cosecant t cotangent t. Okay. So everybody good there? So we can see that there's a lot of similarities between these derivatives here. And once again, these are proven facts, so we can just accept them as theorems. So anyway, and then the derivative with respect to t of what's another one that we have? Another base trig function. SOHCAHTOA, right? Sine, cosine, tangent. So what's the derivative of tangent? Derivative of tangent of t is secant squared of t. So secant squared. Remember, what is secant? Do you remember what secant is? You have to hit the audio button if you want to chime in at home. Secant by definition is 1 over cosine, right? So it's 1 over cosine. So this is actually 1 over cosine squared of t. Right? So the derivative of tangent is secant squared t. So if you know that one, the other thing I can do is cotangent. So what's cotangent? It's 1 over what? What's cotangent? 1 over tangent, right? And tangent is sine of a cosine, so 1 over that is cosine over sine. So the derivative of cotangent t, which is cosine t over sine t. So once again, if I'm taking the derivative of something and it's got a co, what do you think is going to show up? A minus sign. So the derivative of cotangent is minus. And then instead of secant squared, it's going to be cosecant squared. So the derivative of cotangent t is minus cosecant squared t. And of course, cosecant is 1 over the sine, right? So it'd be minus 1 over sine squared t, if you prefer. But anyway, so we have this. Now I'm actually gonna prove this. I don't know if I proved one of these in the video or not. And I got to make sure I don't prove one that you're supposed to do. So ultimately what I expect, because we have limited class time available, we're supposed to meet 5 hours a week all year long or all semester long, right? That's the theory of it. We don't do that. So we ultimately meet ballpark three of those hours out of 5. So you got to watch my videos, but you also got to read the book and try and follow their examples as well, along with that for your learning. But let's just look at the one that's tangent of t. Let's try and prove this. So if we assume that the first two are proven facts, these are actually theorems, or proven facts. So if we just had the first two, could we prove that the derivative of tangent is secant squared? How would we do that? Anybody? How many are you raising? Can you see the board okay at home or not? Or do I need to scoot it in, or what do you want me to do?
I pretty well.
Okay, it's good. All right. So we'll just go with that. So I'm gonna erase these things. These are they are in my video as well. One of my videos in section 2.7. So, but the proof, I don't know if I have a proof in here or not. So let's look at prove that the derivative, I'm gonna change it to an x. ddx of tangent of x, the derivative of tangent of x with respect to x is actually secant squared x. We're gonna prove this. So to prove it, assuming that we know that the derivative of sine is cosine, the derivative of cosine is minus the sine, then what are we going to do? So here's our proof. So we're going to take the derivative with respect to x instead of tangent. What's the definition of tangent? Tangent of x is what? By definition. Opposite over adjacent, but as far as in terms of sine and cosine. Sine over cosine, right? So it's sine, we're taking the derivative of sine of x over cosine of x, correct? Everybody agree? So it's equivalent to that. That's what tangent is sine x over cosine x. So what derivative theorem would we use then? What rule that we learned back in 2.4? Sum rule, product rule, quotient rule. What is this? Sine divided by cosine is a quotient. So we can use a quotient rule on this, can't we? Okay. So if I use a quotient rule, by the way, when I use it, I can put a QR up there with a little circle that shows me, the professor, what you, the student, is doing, right? So what is the quotient rule? Well, the quotient rule says the derivative of a quotient is the bottom one times the derivative of the top one minus the top one times the derivative of the bottom one all over the bottom one squared, right? So if I do that, let's do that. So we start at the bottom, so it's the bottom one, which is cosine of x, right? Times the derivative of the top one. Well, what's the derivative of sine x with respect to x? Derivative of sine is cosine, right? Cosine. So, so it's cosine x times sine x minus the top one, which is sine x, times the derivative of the bottom one. What's the derivative of cosine x? So those are the two we assume that we know. The derivative of cosine is minus, since it was a minus the sine, right? So this is minus sine x times minus sine x all over the bottom one squared. So the bottom one is cosine of x. So cosine of x quantity squared, we can just write as cosine squared x, right? That's how you write it. Instead of having to use the parentheses of cosine x quantity squared, I can just write cosine squared x. So we have this, and then now all I got to do is simplify, right? So this is sine x cosine. Whoa, yeah. Yeah, this is the first time. That's the one. I think so. And something went right because I was working out the brain until I just looked at it. Yeah. Hey, how do I pause the record? How do I back up and delete? Anyway, no. So this is the first time.
The first side. This is the derivative of the sine.
Bottom times derivative of the top. So bottom is cosine times derivative of the top. Derivative of sine is cosine. That?
Yeah.
Minus the top, sine x, times derivative of the bottom one, which is derivative of cosine is minus the sine. Thank you. Yep, there we go. All right, so appreciate that. I'm just assuming that you people at home in your comfy chairs, I can't see that. And the only one that has an excuse, well, there's two people that have a good excuse. So Isaac's got a swollen, like his eyes swollen shut. Carter might be on medication yet. I don't know. By the way, I'm not violating any HIPAA laws because I didn't say your last name. Nobody knows who I'm talking about. Oh, what?
What is this sine squared x?
Well, this is going to be cosine squared x minus sine plus minus times minus is plus sine squared x all over cosine squared x, right? Now, what did you say then?
Sine squared x. Do they cancel?
Well, do they cancel? You got to be a little bit careful because this is a sum up here. So I can't cancel this cosine with this cosine squared with that cosine squared unless I also leave it attached to the other one. So I could rewrite this as 1 plus sine squared x over cosine squared x, which is 1 plus tangent squared x, but I don't want to do that. What's another trig identity that you memorize? What am I trying to make it end up looking like? We said the derivative of tangent is what? Secant squared x. That's what we're trying to prove, right? So this is the final goal, so to speak. So with that, what's secant? 1 over cosine, right? So just look cosine squared x, right? That's what it's equivalent to. Can I make this look like 1 over cosine squared x? Yes, you can. Why? Because sine squared plus cosine squared is 1. So this is equivalent to 1 over cosine squared x, which is, I could rewrite that as 1 over cosine x quantity squared, right? And 1 over cosine is secant. So it's secant squared x. So this is approved. Okay, so that's kind of nice. So if we know that the derivative of sine is cosine and the derivative of cosine is minus the sine, then I just proved that the derivative of tangent is actually equal to secant squared. Okay, and you can actually do this with the I think you can do it with the the last 4 that I wrote up. You should be able to prove it based on the first one, I think. Okay, of course, how would I do the derivative of cotangent x? Well, I'd write it as the derivative of cosine x over sine x and then do the same process, right? But what ends up happening, it'll end up being equivalent to minus 1 over sine squared x, which is minus cosecant squared. Okay, so I'll let you do that one. Do you want to do one more just for fun or not? Or do you want to try it? Okay. Let's do secant. I'm going to let you do secant. And I want you to prove that the derivative of secant is secant x tangent x. So by the way, it is not appropriate for me to just say secant because you can't just have secant. It's always got to be secant of something, right? So when I say secant, I mean secant of x or secant of theta or whatever your dummy variable is. So I want you to prove that the derivative with respect to x of secant of x is secant x tangent x. Okay, so try that. Give you a few minutes. If you get stuck, you can raise your hand or send out a chat. I'm going to check the chat while everybody getting it to work out. What are you rewriting secant as? 1 over cosine of x. And then what rule are you using? Quotient rule, yeah. You could call that cosine to the minus 1 power of x, but then you got to use something called the chain rule, and I don't cover that until I think 2.8. So we don't have that rule yet, but we can come back to this after section 2.8. Anyway, quotient rule, what are you getting then? So it's the bottom one, which is cosine x, times the derivative of the top one, which is what? What's the derivative of a constant? Not nothing.
Or 0.
0, right? So the derivative of a constant, remember, if you graph a constant height, it's a flat line, right? So if you graph f of x equals 1, that's a horizontal line. And the slope of that line at any point is 0. So the derivative of a constant is 0. So that's one of the derivative theorems we had in section 2.4. So it's the bottom one times derivative of the top one, so cosine times 0, which goes away, minus the top one, which is 1 times the derivative of the bottom one, the derivative of cosine is minus the sine, right? So minus the sine of x all over the bottom one squared. So all over cosine squared x. And of course, the cosine of x times 0, that goes to 0, right? And then minus a minus is plus, so it ends up being sine x over cosine squared x. Now that's not the answer. What do we want the answer to be? We want it to be secant x tangent x. So what do I got to do now? Is that equivalent to secant x tangent x?
Yeah.
Why? It is, but why?
Because you 1 over cosine times sine over cosine.
Yeah, I can, this is equivalent to 1 over cosine x times, since it's cosine x squared x is cosine times cosine, right? Times sine x over cosine x. So if I split it out like this, instead of sine x over cosine squared x, I could write it as 1 over cosine x, which is secant x, right? Times, and sine x over cosine x is tangent x. So there you go. There's your proof. And I'm done. Toast is up, right? So there you go. So once again, if we know that the derivative of sine of x is cosine of x, and we know the derivative of cosine of x is minus the sine of x, then we can prove those other 4. So I'll let you go back and try to prove the cosecant derivative as minus cosecant minus cosecant cotangent, and prove the derivative of cotangent is minus cosecant squared. So you can try those on your own as well, knowing the first 2. So we have some of those things which are nice. All right, any questions on that? So let's go over, so those are, I do like proofs, you know, proving them based on what you know. So we can accept those as facts. So those 6 that I wrote up, you need to know off the top of your head without thinking about it. Just like you know the derivative of x to the 5th power is what?
5x to the 4th.
5x to the 4th. You don't even have to think about it, right? It's just that easy. And I'm not making you, by the way, could we prove that? Yeah, we could prove it using the methods of section 2.1 and 2.2, right? The limit is delta x approaches 0 of f of x plus delta x minus f of x over delta x. But then you got x plus delta x quantity to the 5th power. And then you got to use Pascal's triangle, right? So in other words, if I was going to do that x plus delta x to the 5th power, I didn't show you Pascal's triangle, but what's that equal? Anybody know off the top of your head? You don't know that? Like, you can't multiply that out in your head. You don't know that this is x to the 5th plus I think it's 4. 1, 3. Well, how do you figure out your thing? You remember Pascal's triangle? 1, 1, 1. Did they ever teach you this?
Maybe.
Well, it better have.
Just
I'm tired of blaming your parents and your previous teachers. Like at some point in time, you have to be an adult. The time is today. So we got 1, 1, 1, 1, 2, 1. So remember, you add these to get the coefficient for x plus y, right? So you remember this? It's all coming back. 1, 3, 3, 1. 1, 4, 6, 4, 1. And then I'll go one more. 1, 5, 10, 10, 5, 1. And what's this really doing? If I'm looking down this way, this is n here, and this is the coefficient matrix, really, or Pascal's triangle can be used a lot of different ways, but x plus y to the nth power, this is going to give the coefficient, this is n, so the 5th power is the last one, and it will keep going, right? So there's nice patterns in mathematics. But anyway, so then what I can do is I can use these, so the coefficient, so x to the 5th, this is like x plus y to the 5th power, but instead of y, it's delta x. So x gets all 5, the coefficient's 1, and then delta x to the 0 power. But anything to the 0 power is what? 1, except for 0 to the 0 power, which is what, Isaac?
Indeterminate.
Perfect. Man, you're getting good at this game. I love it. I'm smiling under my mask, even though I look pissed off to you. I'm actually smiling. Friday the 13th. You want a scary guy in a mask? Jason. Hopefully you don't know who that is because you're not old enough to watch Friday the 13th horror movies where he chases somebody in a hockey mask and tries to kill them all. All right, but anyway, don't watch that. All right, but anyway, so we got 1 and then 5, and then what? X gets 1 less power, x to the 4, and then delta x to the first, which is just delta x. And then the next coefficient is plus, and it's, by the way, plus, or everything's positive. Otherwise, it alternates signs here. If that was a minus here, it'd be plus, minus, plus, minus. It would alternate. Anyway, so I got this, and then plus 10, and then x gets 1 less of these powers. The total powers is 5 the whole way. So x cubed delta x squared, and then plus 10, and then x gets 1 less x squared delta x cubed, and then plus 5, and then x gets 1 less, so x to the first, which is just x, delta x to the fourth, and then plus 1 times x gets 0, so x to the 0 is 1, delta x gets all 5. So plus delta x to the 5th power. So I beg to differ. You do know how to multiply that out very quickly in your head. And if I was using the limit as delta x approaches 0, f of x plus delta x minus f of x all over delta x, what do we got? We got f of x plus delta x when we have f of x equals x to the 5th power. We did the first part of that. And then minus f of x, we do that. And then we go ahead and subtract all that, simplify it, pull out a delta x, cancel that out, and then let the limit as delta x goes to 0. So if there's a delta x left, it goes away. And we end up getting 5x to the 4th power, thank you. Or we could do it Jack's way and just see it, like Rain Man. Right? So, anyway. Where are you going? You want to do one more? All right, so you know how to do it. Anyway, so we're going to use the easy way, as I say, use the definition. By the way, for anybody that didn't like or struggled with section 2.1 and 2.2, I opened up the keys. So over the weekend, go back to that limit as delta x approaches 0 because you have to know it for the test and kind of review. I know you don't have your assignment back yet, but I'll get that to you. But look at my keys. Those are open. As soon as I get all 2.4, I'll open that too. I'll let you, since nobody's here, we'll just turn in 2.5 and 2.6 Monday, but it better be perfect. I want you to get 100% of your points because you won't on my test. If you do, I'll find something and take it off. All right, but anyway, you want another one? What if I have, here if I've got y equals 1 plus sine x times, well, I don't know, times all over x. What if I have this? I don't need those parentheses, do I? How would you take the derivative of that? What would dy dx or y prime be? You got to use quotient rule, right? So it's bottom one times derivative of top one, derivative of top one, derivative of sum derivative, 0 plus, derivative of sine is cosine, minus the top, 1 plus sine x times derivative of bottom, derivative of x with respect to x is 1 dx dx. 1 all over the bottom one squared, right? So we got that. Then I multiply it out. I got x cosine x minus 1 minus sine x all over x squared. There you go. And just check the answers in the back of the book. By the way, if I want to know what this is when x equals pi over 2, now I can just plug in a pi over 2 and see what the derivative is when x equals pi over 2. Simple, right? So this is for any x. And then if you want a specific one, you just plug it in. So 2.7 is not bad, but you got to learn the derivative. So 1 through 41 odds, if it says numerical derivative, just do the regular derivative. And I'm out of here. I'll stick around for questions, but I'll stop the recording.